Welcome! In this session, we'll tackle LeetCode problem number 2036, maximum alternating subarray sum. This problem challenges us to compute the maximum alternating sum for all possible subarrays of a given array. Let's dive in and explore the approaches to solve this problem step by step. In this problem, you're given an integer array called nums, and your task is to determine the maximum alternating subarray sum that can be derived from any subarray of nums. Now, the alternating sum of a subarray is calculated by assigning alternating signs to its elements as you sum them up. For instance, if you have a subarray A, B, C, its alternating sum is calculated as A, B plus C. Here, subarrays are simply contiguous sequences of elements within the array, and they must contain at least one element. Your goal is to return the highest possible alternating sum of any such subarray. For input, you'll receive an integer array nums with n elements, where each element is an integer. The output will be a single integer representing the maximum alternating subarray sum that can be obtained. Let's look at the first example to understand this better. Suppose you're given the input array nums equals 3, minus 1, 1, 2. The output in this case is 4. To explain why, consider the full array as a subarray 3, minus 1, 1, 2. Its alternating sum is 3 minus 1 plus 1 to 2, which simplifies to 4. After checking all possible subarrays, no other subarray produces a greater alternating sum. Hence, the result is 4. Now, take the second example where the input is nums equals -5, 2, 4, minus 1, 3. In this example, the output is 8. Here, the subarray 2, 4, minus 1, 3 gives the maximum alternating sum. The calculation works out to 2, 4 plus, minus 1, 3, giving us a result of 8. Among all possible subarrays in this array, this one provides the highest alternating sum. Finally, let's look at the simplest possible case with the input nums equals 1. For the input nums equals 1, the output is simply 1. Since the array contains only one element, the only subarray possible is the element itself, and its alternating sum is the value of that element. Moving on to the problem's constraints, the size of the array can range from 1 to 100,000 elements, and each element can range from -10,000 to 10,000. Some important edge cases to consider include arrays with only one element, arrays where all elements are negative, arrays where all elements are positive, and arrays where values alternate between positive and negative. Each of these scenarios can influence the result, so it's important to account for them when designing your solution. To solve the problem of finding the maximum alternating subarray sum, we start by exploring the brute force approach. Here, the idea is to examine every possible subarray in the input array nums. For each subarray, we calculate its alternating sum, where the signs of the elements alternate between positive and negative. To achieve this, we iterate over all starting indices I and, for each starting index, iterate over all possible ending indices j. For the subarray nums I nums j, we calculate its alternating sum by alternating the signs of its elements as we sum them. While this method is straightforward and ensures we consider all subarrays, it has notable drawbacks. The time complexity is O(n) cubed, because we are generating all subarrays and calculating their alternating sums individually. This makes the approach inefficient for large arrays, as the computation becomes unmanageable. Additionally, the space complexity is O(1), which is efficient, but the excessive time complexity renders this method impractical for competitive programming scenarios. Recognizing the inefficiency of the naive brute force approach, we can optimize it by avoiding redundant calculations. Instead of recalculating the alternating sum from scratch for each subarray, we can compute it incrementally. In this optimized brute force approach, we use a nested loop to iterate over all subarrays, but instead of recalculating the sum for each subarray, we maintain a running alternating sum as we iterate through the elements of the current subarray. This allows us to update the alternating sum dynamically without repeating previous calculations. As a result, the time complexity is reduced to O(n squared), which is a significant improvement over the cubic time complexity of the naive approach. However, it is still quadratic, which makes it less suitable for very large arrays. The space complexity remains O(1), since we only need a few variables to track the running sum and the maximum sum encountered so far. While faster than the naive method, this approach is still not ideal for competitive programming due to its quadratic growth. To further improve efficiency, we can use a dynamic programming approach by leveraging the recursive structure of the problem. The key insight is that the alternating sum of a subarray ending at index j can be derived from the alternating sum of a smaller subarray ending at index j1. To formalize this, we define two arrays, dp_even j, which represents the maximum alternating sum of a subarray ending at index j with a positive sign for the last element, and dp_odd j, which represents the maximum alternating sum of a subarray ending at index j with a negative sign for the last element. Using these definitions, we can establish the recurrence relations dp_even j equals nums j plus dp_odd j1 and dp_odd j equals nums j plus dp_even j1. The base case is straightforward. For the first element, dp_even 0 is simply nums 0 and dp_odd 0 is nums 0. By iterating through the array and applying these recurrence relations, we can compute the alternating sums efficiently. At the end, the result is the maximum value across all dp_even j and dp_odd j. This approach has a time complexity of O(n), because we process each element once, and a space complexity of O(n) to store the dp_even and dp_odd arrays. To make the dynamic programming approach even more efficient, we can reduce its space complexity. By observing that dp_even j and dp_odd j only depend on their values from the previous index, we can eliminate the need for maintaining entire arrays. Instead, we use two variables, prev_even and prev_odd, to store the values of dp_even and dp_odd from the previous step. As we iterate through the array, we update these variables iteratively, ensuring that we always have the most recent values needed for the calculations. This optimization reduces the space complexity to O(1), while maintaining the time complexity at O(n). Ultimately, the space-optimized DP approach is the best choice for this problem. It strikes the perfect balance between efficiency and simplicity, making it highly scalable to large inputs. While the brute force methods are easier to implement, their inefficiencies render them impractical. The dynamic programming approach, particularly with space optimization, leverages the problem structure to provide an optimal and elegant solution. In this problem, we are tasked with finding the maximum alternating subarray sum for a given array of numbers. The alternating sum for a subarray means calculating the sum where the signs of the elements alternate. For example, in a subarray like A_1, A_2, _3, the alternating sum would be A_1, A_2 plus A_3. To solve this, we'll use a dynamic programming approach. First, let's understand the behavior of alternating sums. For each subarray, the pattern starts with the first element being positive, followed by alternating between negative and positive signs. For instance, if nums equals 1, 2, 3, the subarrays would have alternating sums like 1, 4, 1, 1 to 2 equals dash 1, 4, 1, 2, and 1, 2 plus 3 equals 2, 4, 1, 2, 3. Similarly, 2 is just 2, 2, 3, gives 2, 3 equals dash 1, and 3 is 3. This alternating property is vital to our solution, as we'll build a dynamic programming strategy to efficiently calculate these sums for all subarrays. Now that we understand the pattern, we define our state variables. We'll use two dynamic programming arrays, dp_even and dp_odd. dp_even I represents the maximum alternating sum of subarrays ending at index I, where the last element has a positive sign. Conversely, dp_odd I tracks the maximum alternating sum for subarrays where the last element has a negative sign. To start, we initialize the base cases. At index 0, the only subarray is the single element itself. So, dp_even 0 is simply nums 0, because the first element is treated as positive. On the other hand, dp_odd 0 is 0 since no subarray can end with a negative sign at the start. Moving forward, we use a transition relation to update these arrays. For dp_even I, we have two options: either start a new subarray at I, which means nums I alone, or extend an existing subarray where the previous element at I1 had a negative sign. This gives us the formula dp_even I equals max nums I dp_odd I1 plus nums I. For dp_odd I, the transition is similar but with signs flipped. Here, we also have two choices: start a new subarray at index I, which would contribute nums I, or extend an existing subarray where the previous element at I1 had a positive sign. This leads to the formula dp_odd I equals max nums I dp_even I1 nums I. Once we've iterated through the array and filled both dp_even and dp_odd, the result is simply the maximum value across all indices in these arrays. Mathematically, we calculate result equals max dp_even max dp_odd. This ensures we capture the highest alternating sum for any subarray configuration. By maintaining these two arrays, we efficiently handle the alternating sign transitions. This approach ensures that, at every step, we only focus on the local optimal choice for extending or restarting subarrays, which avoids unnecessary recomputation and speeds up the solution. To implement this, we rely on dynamic arrays, specifically dp_even and dp_odd, to store intermediate results for subarrays ending at each index. Additionally, we maintain a result variable to track the global maximum alternating sum. In terms of complexity, the time complexity is O(n), since we process each element of the array exactly once, updating dp_even and dp_odd in constant time per index. The space complexity is O(n), due to the storage of the two arrays, but we can optimize this to O(1) by using two variables instead of full arrays, as we only need the previous states at any given time. Finally, consider edge cases like single-element arrays, where the alternating sum is the element itself. For arrays with all positive or all negative elements, the alternating sum may require skipping elements to maximize the result. And for mixed sign arrays, the transition logic ensures we handle changes in sign correctly. These insights highlight the efficiency and versatility of the dynamic programming solution for this problem. The provided code solves the problem of finding the maximum alternating subarray sum efficiently using a dynamic programming approach. The key idea is to maintain two variables, max_even and max_odd, which represent the maximum alternating sums ending at even and odd indices, respectively. The algorithm iterates through the array nums. For each element, it updates max_even and max_odd based on whether the current index is even or odd. If the index is even, max_even is updated to be the maximum of the current element or the sum of the current element with the previous max_odd. Similarly, if the index is odd, max_odd is updated to the maximum of the negative current element or the sum of the negative current element with the previous max_even. At each step, the global result is updated to ensure it captures the maximum value among max_even, max_odd, and the current result. This ensures that the algorithm considers all possible subarrays while maintaining an optimal time complexity of O(n), where n is the length of the input array. The algorithm initializes max_even and max_odd to -infinity to handle edge cases where no subarray has been processed yet. The final result is returned as the maximum alternating subarray sum. Here, we start by defining a class called solution and creating a method named maximum alternating subarray sum that accepts an integer array called nums. The first step is to determine the length of the input array, which we store in the variable n. Next, we initialize three key variables, max_even, max_odd, and result. The max_even variable will track the maximum alternating subarray sum ending at an even index, while max_odd will do the same for an odd index. Both are initially set to integer.min_value to ensure any valid sum will replace them. The result variable will store the overall maximum alternating sum we calculate across the array. We then enter a for loop to iterate through all indices of the array. For each index I, we check whether it is even or odd using the modulo operator. If the index is even, we calculate a new max_even value. This value is the greater of the current element nums, I, or the current element added to max_odd, provided max_odd is not still at its initial value. We then update max_even with this new value, while carrying forward the previous max_odd value unchanged. If the index is odd, we calculate a new max_odd value instead. This value is the maximum of the negation of nums, I, or the negation of nums, I, added to max even, as long as max even is not still set to its initial value. After updating max odd with this new value, we carry forward the previous max even value unchanged. At the end of each iteration, we update the result variable to reflect the maximum value seen so far between max even and max odd. This ensures that result always holds the highest alternating subarray sum encountered up to the current index. Once the loop completes, we return the result, which represents the maximum alternating subarray sum for the entire input array. With this implementation, we efficiently compute the desired result in linear time, making it suitable even for larger input sizes. To solve the problem, we start by initializing three variables, max_even, max_odd, and result, all set to -infinity to represent the worst-case scenario. The length of the input array nums is 4. In the first iteration, we look at the element at index 0, which is 3. Since the index is even, we calculate the new value of max_even as the maximum of the current number, 3, and 3 plus the previous max_odd value if it exists. Since max_odd is still -infinity, the calculation simplifies to just 3. Max_odd remains unchanged, and the result is updated to the maximum of its current value, max_even, and max_odd, which gives us a result of 3. At this stage, our state is max_even equals 3, max_odd equals INF, and result equals 3. Next, in the second iteration, we examine the element at index 1, which is -1. Since the index is odd, we calculate the new value of max_odd as the maximum of the positive version of this number, which is 1, and 1 plus max_even if it exists. Here, max_even is 3, so the calculation gives us max_odd equals max, 1, 1 plus 3, resulting in 4. We carry forward the value of max_even, which remains 3, and update result to the maximum of its current value, max_even, and max_odd. This gives us a new result of 4. In the third iteration, we move to the element at index 2, which is 1. Since the index is even, we update max_even to the maximum of the current number, 1, and 1 plus the previous max_odd value, which is 4. The calculation gives us max_even equals max, 1, 1 plus 4, resulting in 5. We carry forward max_odd, which stays at 4, and update result to 5. At this stage, our state is max_even equals 5, max_odd equals 4, and result equals 5. In the fourth iteration, we analyze the element at index 3, which is 2. With the index being odd, we calculate the new value of max_odd as the maximum of the negative version of this number, which is -2, and -2 plus the previous max_even value, which is 5. This gives us max_odd equals max, -2 plus 5, resulting in 3. The value of max_even remains unchanged at 5. We then update the result to the maximum of result, max_even, and max_odd, which keeps result at 5. At the end of this example, the final output is result equals 5. Now, let's consider a second example where the array is nums equals, -5, -2, -3, 7. As before, we start by initializing max_even, max_odd, and result to -infinity, and the length of the array is 4. In the first iteration, the element at index 0 is -5. Since the index is even, we calculate max_even as the maximum of -5 and -5 plus the previous max_odd value, which is -infinity. This simplifies to max_even equals -5. The max_odd value remains unchanged, and we update result to the maximum of its current value, max_even, and max_odd, giving us result equals -5. In the second iteration, we analyze the element at index 1, which is -2. With the index being odd, we calculate max_odd as the maximum of the positive version of this number, 2, and 2 plus the previous max_even value, which is -5. This gives us max_odd equals max, 2 to 5, resulting in 2. The value of max_even is carried forward as -5, and result is updated to 2. In the third iteration, we look at the element at index 2, which is -3. Since the index is even, we calculate max_even as the maximum of -3 and -3 plus the previous max_odd value, which is 2. The calculation gives us max_even equals max, -3 plus 2, resulting in -1. We carry forward the value of max_odd, which remains 2, and update result to the maximum of its current value, max_even, and max_odd, keeping result equals 2. In the fourth iteration, the element at index 3 is 7. As the index is odd, we calculate max_odd as the maximum of the negative version of this number, -7, and -7 plus the previous max_even value, which is -1. This gives us max_odd equals max, -7 plus -1, resulting in -1. The max_even value remains -1, and result is updated to 2. At the end of this example, the final output is result equals 2. For the third example, the array is nums equals 10, -10, 20, -20, 30. We start by initializing max_even, max_odd, and result to -infinity, and the length of the array is 5. In the first iteration, the element at index 0 is 10. Since the index is even, we calculate max_even as the maximum of 10 and 10 plus the previous max_odd value, which is -infinity. This simplifies to max_even equals 10. The max_odd value remains unchanged, and result is updated to the maximum of its current value, max_even, and max_odd, giving us result equals 10. In the second iteration, the element at index 1 is -10. As the index is odd, we calculate max_odd as the maximum of the positive version of this number, which is 10, and 10 plus the previous max_even value, which is 10. This gives us max_odd equals max, 10, 10 plus 10, resulting in 20. The value of max_even is carried forward as 10, and result is updated to the maximum of max_even, max_odd, and its current value, resulting in result equals 20. In the third iteration, the element at index 2 is 20. Since the index is even, we calculate max_even as the maximum of 20 and 20 plus the previous max_odd value, which is 20. This gives us max_even equals max, 20, 20 plus 20, resulting in 40. We carry forward the value of max_odd, which remains 20, and update result to 40. Next, in the fourth iteration, the element at index 3 is -20. With the index being odd, we calculate max_odd as the maximum of the positive version of this number, which is 20, and 20 plus the previous max_even value, which is 40. This gives us max_odd equals max, 20, 20 plus 40, resulting in 60. The value of max_even remains 40, and result is updated to 60. Finally, in the fifth iteration, the element at index 4 is 30. Since the index is even, we calculate max_even as the maximum of 30 and 30 plus the previous max_odd value, which is 60. This gives us max_even equals max, 30, 30 plus 60, resulting in 90. We carry forward max_odd, which remains 60, and update result to 90. At the end of this example, the final output is result equals 90. To analyze the time complexity of the solution, let's consider how the algorithm processes the input array nums. It uses a single for loop that iterates through the array from the first index to the last. For each index, the algorithm performs a constant amount of work. Specifically, it calculates the new values of max_even and max_odd using the max function, which is an O1 operation. Additionally, it updates the global result variable with another max operation, which is also O1. Since the loop runs exactly once for each of the n elements in the array, and each iteration involves a fixed amount of work, the total time complexity of this solution is O(n). This makes the algorithm highly efficient for determining the maximum alternating subarray sum. Now, turning to the space complexity, this algorithm is highly space efficient. It uses only a fixed amount of extra memory, regardless of the size of the input array. The key variables used include max_even and max_odd to track the maximum alternating subarray sums for even and odd indices, a result variable to store the maximum result found so far, and n to store the length of the array. Since none of these variables scale with the size of the input array, the space complexity is O1. Furthermore, the time complexity remains consistent at O(n) for all cases best, average, and worst, since the number of iterations is strictly determined by the size of the input, and each iteration involves the same constant amount of work. The algorithm's performance is robust and unaffected by the specific distribution of values in the array. Comparing this optimized solution to a brute force approach highlights its efficiency. A naive method would involve evaluating all possible subarrays of the input array and calculating their alternating sums. For an array of size n, there are O(n squared) subarrays to consider, and calculating the alternating sum for each subarray would require O(k) operations, where k is the length of the subarray. Combining these factors results in a total time complexity of O(n cubed) for the brute force method. In contrast, the optimized algorithm avoids redundant calculations by dynamically maintaining the max_even and max_odd values as it iterates through the array. This ensures each element is processed exactly once, with only O(1) work per element. As a result, the total time complexity is reduced to O(n), a dramatic improvement over the brute force approach. In conclusion, the optimized solution significantly outperforms the brute force approach in both time and space complexity. While the brute force method requires O(n cubed) time and potentially O(n) or more space for auxiliary computations, the optimized solution achieves O(n) time and O(1) space. This makes it highly scalable and well suited for large input sizes, such as arrays with up to 100,000 elements. In scenarios where the brute force approach would be computationally prohibitive, the optimized solution provides a practical and efficient means of solving the problem. One common pitfall in solving the maximum alternating subarray sum problem is mismanaging the alternating sum calculation. The key is to remember that the first element always contributes positively, and the sign alternates for subsequent elements. If you fail to track these signs properly, the subarray sums will be off. To avoid this, explicitly maintain a variable to track the current sign as you compute the sum. Another frequent mistake is using a brute force approach to calculate sums for all possible subarrays. While this may work for small arrays, it quickly becomes inefficient for larger inputs since it requires O(n cubed) time due to nested loops. Instead, consider optimized approaches, like dynamic programming or sliding windows, to cut down on unnecessary calculations. Lastly, special cases like arrays of size 1 or arrays with uniform elements often trip people up. These edge cases, if not handled explicitly, can lead to index errors or inaccurate results. Always include specific checks for these scenarios before running your main algorithm. Another common mistake to watch for is ignoring negative numbers in the array. It's easy to assume all values are non-negative, but this can lead to incorrect sign adjustments in cases where negative elements are included. To handle this, ensure your algorithm accounts for both positive and negative values, maintaining the proper alternating sum logic. Additionally, improper initialization of key variables like the maximum sum can result in missed optimal subarrays, especially at the start of the array. If you initialize the maximum sum to 0 or some arbitrary value, you might overlook subarrays that start with smaller numbers or negative values. To avoid this, always initialize your max_sum variable to the smallest possible value, such as -infinity, giving your algorithm a correct baseline for comparisons. When preparing for interviews, it's important to understand the underlying patterns in alternating sum problems. These problems often leverage dynamic programming or prefix sum techniques, so be ready to explain why you chose a specific approach. Interviewers typically look for efficiency, so you should identify and address inefficiencies right away. For instance, if your initial solution is O(n cubed), discuss how you could optimize it to O(n squared), or even O(n). It's also critical to clarify the exact problem definition with the interviewer, especially for concepts like the alternating sum, which could start with either a positive or negative sign depending on the question. Highlighting edge cases, such as single-element arrays or arrays filled with all negative numbers, demonstrates your thoroughness. Lastly, discuss trade-offs between time and space complexity. For example, dynamic programming might use extra space but can significantly improve runtime, showing you understand the balance between these factors. This problem is closely related to other well-known LeetCode problems, which can provide valuable insights. For example, LeetCode 1911, maximum alternating subsequence sum, is very similar but deals with subsequences instead of subarrays. LeetCode 53, Maximum Subarray, is a classic problem that utilizes Cadon's algorithm, which you might adapt for certain variations of alternating sums. LeetCode 152, Maximum Product Subarray, involves handling alternating products instead of sums, which introduces its own challenges but shares some conceptual overlap. Lastly, LeetCode 1746, Maximum Subarray Sum after one operation, explores constrained subarray calculations, requiring careful thought about optimization and edge cases. Studying these related problems can help broaden your understanding of techniques and strengthen your problem-solving skills. There are several alternative approaches you can use to solve the maximum alternating subarray sum problem, each with its own trade-offs. A dynamic programming approach works by maintaining two states for each index, the maximum alternating sum ending in a positive sign and the maximum alternating sum ending in a negative sign. This method achieves O(n) time complexity but may require extra space to track these states. Another option is the sliding window technique, which involves using a fixed size window to compute alternating sums for subarrays of a specific length. While this method is simple to implement, it may not be suitable for cases where subarray lengths vary. Finally, the prefix sum approach precomputes cumulative sums, allowing you to quickly calculate alternating sums for any subarray. This reduces computation time but requires O(n) extra space. Choosing the right approach depends on the problem constraints and the trade-offs you're willing to make between time and space complexity. Great work! We've successfully explored the solution to maximum alternating subarray sum. Remember, understanding the problem and optimizing for time and space complexity are critical. Thank you for watching, and don't forget to like and subscribe for more insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!